what I'm happy to be here to talk about is some recent work that we've been doing with the MVAPICH team in the spirit of, let's see if this works, in the spirit of is this working? No, I had to do it. Mascots. I want to show our mascot. So this is really a duck and buckeye relationship that I'll be talking about. I'll start out with some acknowledgments because this is supported by an NSF award that is specifically focused on the integration of MVAPICH and TAO using the new MPI Tools Interface, which DK mentioned earlier in his talk. The people who are really doing the work are shown here, and I just get to make the presentation. And Srinivasan and Aurel are here in the audience, and Samir is, I think, in New Zealand today. So this is what I'd like to try to do in the talk, is to tell you about what we've done, but motivate this through the fact that we see increasing complexities not only in the parallel software stack but also in the HPC systems, and that we need to try to improve the support that we have for doing performance optimization and tuning. One of the opportunities that we have is to use, with respect to MPI, is to use the new MPIT interface. So I'll tell you about that. I'll give you a brief introduction to TAO, talk about some of the performance engineering outlook that we can imagine using MPIT with the integration of TAO and MVAPICH, and give you some case studies and then wrap up. Okay, well, software stack, parallel software stack is becoming more complex, and in particular the message communications runtimes are complex systems, and they are needing to address some of the complexities that we find in the HPC platform. They themselves are complex pieces of code, multiple components, and they interact in different ways, for different applications. So it's not just the library, it's how the application uses that library and interacts with the underlying system. This is not going to get any better. It's going to be harder down the line. So improving the performance in MPI is important. Trying to engage in a performance engineering process that couples not only the MPI's implementation, but also how the applications are using that implementation is important too. We need to evolve the way that we do this. We need to involve not only our tools for doing the performance engineering, but what is within that software system that allows us to get information to do that job well. And that's what I'm going to talk about. We'd like to leverage the MPI Tools Interface and then have a deeper integration using that interface between other components that can help to address performance engineering problems. So you might say, well, what's wrong with the MPI profiling interface? And after all, it was a brilliant forethought in the MPI, or the originator, to think about having this mechanism by which we can look at MPI operations by just wrapping the interface, wrapping the interface of the MPI routine, and then at that time capturing information about the use of the MPI routines. And to tell you the truth, that was great. It was a brilliant idea, and it has been extremely useful in the performance community for looking at MPI behavior, identifying places where we have problems, tracking message communications throughout the application, looking to see where we have opportunities for doing some performance tuning. PMPI supports performance engineering with respect to that. Looking at time, where time spent, how many times we call a particular routine, and so forth, tracking the message communication, getting information about message size, and all of that. And it has been very productive. But it is only an application level, an external view. It doesn't really give us enough of what we would like. And I think the MPI committee and forum looked at that and said, we need something more. We need to look underneath the covers, so to speak. And so with the MPI 3.0 standards, MPIT, a tools interface, MPI tools interface was defined. And that was great. It really tried to improve on what were more ad hoc mechanisms for doing this in the past by giving real definition of what could be looked at within the MPI implementations and what also could be controlled. So we have the idea of there being performance variables and control variables, where the performance variables are essentially trying to report or expose information about things that are going on within the MPI implementation, static things and dynamic things that are taking place. And such as counters and metrics and state information, things might be related to or important to performance. These are exposed by that implementation, and then some external tool or you shouldn't necessarily think of it external, but some tool that is running as part of that code can then look at that information. Great. Okay. CVARs are taking the opposite functionality, whereby they are they are variables that are important for some purpose within the MPI implementation, and they can be set and controlled and both, again, statically and dynamically through the MPI interface. And it is that tool on the other side of the interface that is doing this. Okay? Each implementation of MPI exposes their particular PVARs and CVARs, allowing some customization for that particular implementation, and we use MPIT then to do it, so to speak. So the PMPI interface is really not giving us an opportunity to look at the internals of MPI, but MPIT does. It gives us a window on that. It's standardized as part of the standard. MPI implementations, and I think this is a benefit, are free to decide what it is that's important for them to expose. And the tool has support within the MPIT to discover what that PVARs and CVARs are. There is, as you might expect, some logic that will likely need to be put into the tools to understand how to work with that for that particular MPI implementation, but it's there. It's rich information. It can be rich information. What's important to understand is that, like other MPI routines, it's a rank level view. That is, just like in PMPI, you're looking at some functionality at the rank level. Okay, and I'll come back to that a little bit later. We can expose control. That's important. It's also kind of cool that the fact that this particular definition allows you to bind these PVARs and CVARs to particular MPI objects, and that's interesting. So there's a lot of thought that was put into MPI Tools Interface. And there have been implementations. These are some of the implementations that you see. I've characterized this by just the number of things that you have in the implementations, at this moment in time. And it changes, and you would expect it to change because these are different implementations. And you see, that there even are some cases where performance variables are not provided. There are cases where a really large number of control variables are provided. Let's see if I can get this to work here as an open MPI. And in part, this is because they made some decisions to export what they call these MCA parameters to CVARs. And so they already had something within those implementation that were serving a similar purpose, for instance. And that's good. That's good to see. Under MVAPICH, we see the current state here. There's more additional CVARs that are being added as well. And just to say, sort of like a precursor here, Tao is working with MPICH, Intel, MPI, and MVAPICH in each of those implementations. Okay, so let's look at more MVAPICH MPT. The PVARs, these are showing some of the things that are being exposed through the interface that you can get information about, that a tool can get information about, and also things that can be controlled. Collective algorithms, different modes, and various aspects of garbage collection and so forth, and control for VBus and so on. Now, some of these variables are static in the sense that they might be set at initialization time, MPI init. Some are changing dynamically. You might expect that for the performance variables, and can be changed, controlled dynamically with the with the CVARs. Okay. How do we do that? How do we use that? Well, the interface is supporting that for us. It defines the interface, the semantics, how you use it, how do you program it, process and procedure, and, data types and parameters, and all of that. It's a real interface. And that's great. The tools use that interface. They get information about what PVARs and CVARs are there for them to use. They then can read those performance variables, and they can do things with that information through the ways in which that interface provides that to happen. They can get incorporated into whatever they want to incorporate it into. And they can set control variables to specify MPI operations or change that during the execution. Again, this is a rank level interface. It's like other routines. You're working with respect to a rank. It might be that you're using some of the binding functionality to bind with respect to objects within that rank and so forth. Okay? And it also allows, which is also interesting, multiple tools to be using the interface in flight at the same time. So that's neat. One of those tools is Tau. It's a very brief introduction. Tau, in some respects, like MVAPICH, is a long-running project. I think we had them beat on the number of years. We're about 25 now, 24, 25. It is attempting to be a performance problem-solving framework as well as an open-source implementation of measurement and analysis tools for almost practically any type of parallel programming environment that you can think of. At least we like to think so. Okay? It supports measurement and analysis. It supports some data mining tools and auto-tuning tools and so forth. This is the architecture. It is intended to be used in combination with your application to gather performance information of various sorts and types, to collect that through parallel profiles and traces, and then to provide some analysis post-mortem, as well as trying to do some of that online, which I'll talk about a little bit later. The different types of components then in these instrumentation, measurement, and analysis are trying to cover the entire field of parallel software and systems, and you can see all the different types of things that Tau is supporting there. Okay, let's get back to MPI performance engineering then. We want to try to improve the performance of MPI implementations. How would we go about doing that? And how can MPIT help in this goal? So MPIT is there to provide an interface between the MPI implementation and the tools, performance tools like Tau that might want to work with MPI applications. And we have been working with MPI applications for a very long time using PMPI. But now we have the opportunity to get more information about the MPI implementation itself and perhaps provide through our technology a way to build additional capabilities within the tools to help to control the MPI operation. That's the idea. That's the idea. So the types of engineering methods that we could accomplish would be those that do some measurement and analysis, try to do analysis of certain MPI performance that leads to optimizations and recommendations, and those get incorporated within the execution to set control variables under particular conditions. We can do that in an online manner through runtime introspection and some auto-tuning, as well as performance monitoring across MPI ranks, because remember, MPIT is only a rank level interface. If we want to look something across the application as a whole using MPIT, we need to do something to gather that information and do something with it, and then have maybe some global control that then filters down through the MPIT interfaces to control the individual ranks. Okay, so that's what we're going to look at, hopefully through a couple of demonstrations here. Let me give you, though, a picture to try to keep in your mind as to what exactly is going on. So we have these two libraries. Tau is implemented as a library too. And these two libraries are being interfaced through MPIT. MVAPICH is providing the PVARs and CVARs. tau on this side is using the MPIT interface as well as a way to read those and to set those CVARs. It uses its already existing measurement and analysis infrastructure. We've done some additional extensions that would then allow for things at runtime to be set through the MPIT interface for CVARs, and we're trying to support online analysis and at the node level, at the rank level, as well as the global level. So these two things are shown in a dotted boundaries, and I'll talk about them more in a bit. So let's, what can we do? Well, using tau, using MPIT interface, we can just read the PVARs. We can query those PVARs at regular intervals. For instance, using some signal handler, going in, using the interface, grabbing all the PVARs that we can, pull them into our whole profiling measurement infrastructure that's already there existing in tau. You can't read this hardly at all, but here are the PVARs. Do some analysis of that and provide that post-mortem to the application's execution so that you can look at it, interpret it, and maybe do some other things with it. Pretty straightforward. So that's a good step forward. Now let's look at something a little bit more complex. First, talking about the applications that we use for the case studies. Amber MD, 3D Stencil, and Mini MR. You can see what their description is here. Here what we're looking at is a stencil-based code. These two are that nature. And then Mini MR, which has different types of performance characteristics that we want to try to understand a little bit better. So let's start with Mini MR. First, I'll tell you about the experimental setup. This work has been going on for about 1.5 years, and we do have implementations that we've done using MPIT, and so these are running on some clusters per Stampede that we are using. In all these experiments, we're having one MPI rank per node, per core, using the affinity settings. So we're running on Stampede as well as the RI2 cluster here at Ohio State. This one is being used for Amber MD, and this particular machine is being used for the other two applications. Okay, so let's start off with Mini AMR. One type of optimizations that MVAPICH is supporting is the offloading of all reduced to network hardware using a Sharp protocol. Under what conditions might you want to enable this? Well, we can make measurements using MPIT to collect average message size involved in MPI all reduce operations. In fact, some of these measurements are also incorporating other support that we have through PMPI to make certain measurements. And then we can also collect time spent in all reduce versus overall execution time, and we can analyze that data. So if we analyze it, we might say, hey, if the message size is below a certain threshold and the percentage of the runtime spent in MPI reduce is above a certain threshold, this could trigger possible recommendations that we might want to make to use the Sharp protocol. Well, how do we do that? We do that using MPIT control variables exactly for that purpose. So what we see here is we see a pair prof display of those measurements, and then we've incorporated within the parallel profile analyzer, the pair prof profile analyzer, a recommendation system that looks for the particular features within that performance measurement and says you could see potential improvements in performance by configuring MVAPICH with this dash enable Sharp and enabling this CVAR at execution time. So the idea is to make measurements, utilize the fact that we have that interface now to provide a recommendation, a recommender system, incorporate that within the next execution of the run, and here what we see are the results. The default setting has an execution time of 648, but when that Sharp is enabled, then we have a reduction in the execution time. So simple, but we didn't really have that way to do this before in some standard manner. Here's another application. You got to tell me how much time I have left. Doing okay? Where we're looking at an interesting interaction between setting of eager limit and the freeing of unused buffers. So MVAPICH uses internal communication buffers to temporarily hold messages yet to be transferred for point-to-point communications. These VBuff pools vary in different sizes, and at runtime then MVAPICH matches based upon the size of the message and the VBuff pool. And okay, so in particular, VBuffs are used to send short messages in an eager manner to reduce communication latency. Okay, and longer messages use rendezvous protocol without VBuffs. Great. Now, if we use an eager protocol, then it's possible that we will have an increase in the amount of memory used by the VBus because we're trying to leverage that as well as a way to get performance improvements. Increasing in this memory for VBus could potentially have another effect, which will reduce performance just maybe because of the amount of memory being used for VBus. And so we want to make sure that when we try to apply this optimization that we're not somehow negatively impacting other things. So we're going to monitor and control the usage of virtual buffers. We have a way to do that now with MPIT. We look at virtual buffers as offering that improvement possibility, but we really want to see if there are other opportunities as a result that we could further optimize. MVAPICH has defined a number of PVARs that are monitoring current usage levels, availability of the free buffers, different buffer pools, and so on and so forth. And a tool using MPIT could access that information and reason about it to make some decisions about whether we could, whether things are going well or not. In addition, it exposes some CVARs that allow us to free these buffers, VBuffs, at runtime. Okay, so we can use that mechanism now in order to check to see whether the usage of the VBuff pools are varying in time between the processes and if they're being negatively affected because we happen to be using an eager protocol and so forth. Here's the PVARs that are of interest to us and the CVARs of interest to us. And the idea is that we need to look to see if increasing the eager limit could lead, which improves the overlap communication, computation could, have some effect in terms of increased memory sizes that we could help to reduce. So we can make some measurements, and here's some measurements that are showing actually a trace of the utilization of versus tau user, which is essentially running computation, and MPI. Okay. In the case on the left, we have this distribution of utilization before an eager threshold tuning occurred. And on the right, we are looking at that utilization when the eager threshold tuning has been applied. Now, this eager threshold tuning, again, is being done through control via the MPIT interface. Okay? And so we see the improvement that comes from that eager threshold tuning in a reduction the increase in the communications and the computation overlap, which is being used as our optimization metric here. But we also see that there's a significant increase in the amount of VBuff memory that is being used. Well, perhaps if we look at that VBuff memory usage, we might say to ourselves, wait a minute, maybe there's some ways that we can reduce the amount of VBuff usage, particularly when there are VBuffs that are not being used, as part of this sort of side effect or support for this eager threshold tuning. And identifying that then allows us a second optimization to go and reduce those unused VBuffs. And this is showing what happens when we do so. We maintain, in fact, we even improve a little bit the communications computation overlap, but we significantly reduce the amount of VBuff storage that is being used because it's not being used. we see this come up. 3D stencil is really kind of this skeleton application just to try to give us a way of playing around with stencil codes with this type of behavior. But you see this behavior in Amber MD. And what you see in these two graphs is that we see what happens when the eager threshold is applied. We see the increase that takes place. Again, this is just as a trace. We're just sampling. We're just using MPIT to look at these variables associated with VBuff usage, and we see the increases that are occurring. Okay, but we can then free these VBuffs if they are being unused, and we see an associated drop. This is just to give you a sense of what you're seeing relative to the fact that we can now look during execution at what these performance variables are telling us. So Amber MD demonstrates this particular behavior. It has an increase in the virtual buffers that are being used, but in fact a certain proportion of them are unused. And now we can check that out during the execution and free that virtual VBuff memory to have some savings. And that's what we did. So in this particular example, it was used as a demonstration to show that we can have some online additional tuning that comes by just monitoring certain variables where we know that they could be further optimized, certain things could be further optimized. And so we did that. We looked at this first, setting the eager threshold right at the beginning in MPI init, and then looking at what the effect that had, monitoring the increase in virtual buffer memory usage, and then dynamically trying to free the ones that we identified as being unused. And that's what you see here in this particular table. What we have is the application runtime being significantly improved by the eager threshold setting and the associated increase in the amount of virtual VBuff memory. But then with the auto-tuning that we had in Tau, we could reduce that, monitoring the VBuff usage and getting rid of the ones that were not being used. All right, so what you see here are an example where we are using a tool, performance tool like Tau, to gather information about the internal operation of MPI through the MPIT interface. The way we do that in Tau is just to set up some interval timer that invokes a signal handler that just then goes and reads particular p-vars of interest to us at those interrupt boundaries. Pull in that information, incorporate it into our measurement infrastructure that we already have within Tau, and even at that time maybe calculate some statistics. Then what do we do? Then what do we do with the data? Well, Tau can provide complete application performance data for offline analysis. This just gets incorporated into that in the formats that we use for performance data. But we also might want to take some actions online. And some of the extensions that we are looking to make in Tau are particularly for that purpose. This just happens to converge quite nicely with this project, with an MPIT project, because there's a real motivation for thinking about using performance information online. So we are extending Tau with capabilities that allow for those performance introspection and policy-driven decisions about what you're seeing with respect to the performance behavior. And this is being implemented in the context of this project. So this is work that is being done by Srinivasan, who is here. And so the idea, again, is that we have some way in which we can extend Tau through some plug-in type of interface that does performance introspection, analyzes performance state, may decide to take some action, and in the case of MPIT, it has all those support in order to do that, reading of p-vars, setting of control variables. And this is what we've tried to utilize in the example that I just described. This is one type of runtime monitoring and tuning. But again, I want to emphasize that the MPIT interface is only giving you a way to look at rank level information and do control at the rank level. It does not tell you the interface, that particular interface that you're using, about the entire application. But you can use something else to gather all that information and tell you something about the entire application. And that's interesting. But we have to augment what we have in our tools in order to do that. So the global monitoring for application control is also something that we're looking at. We're looking at global performance introspection and support within that monitoring framework to allow for control to take place. We're doing it in two respects. One came out of the Argo project from the DOE called Beacon, stands for Backplane for Event and Control Notification. And we're also building another one called Scalable Observation System from our Mona project. And Aurel is here, who has been the Beacon developer, and he can tell you more about that in particular. What we've done with MPIT is that we've essentially exposed from, let's see, how does this go? From tau, information that we've gathered on a per rank basis to Beacon. So it sees all the ranks, all the PVARs from all the ranks that are running as part of the application, and it can do something with them. It can go and do some analysis. It can show you this in terms of a presentation. It can do all this, but it's collectively doing this across the system. Okay? And this is just showing you one of the interfaces that we call PyCooler for analysis and visualization and for doing control. It could set one of these CVARs globally, and that could then go back through Beacon, through tau, through MPIT, to MVAPICH to set that control variable for all of them. See the poster on both of these two things. So in conclusion, we have this great opportunity to work with OSU on this project. And we still have about 2 years left on it. So we're working hard. The base functionality is in place. There are enhancements being made both in MVAPICH on their side of the MPIT interface, as well as on our side to add some analysis functionality, monitoring, and online tuning. There are real compelling reasons here to consider the integration of performance analysis tools and optimization that can bring throughout parallel software stack, not just at the message communication level, but throughout all things. We are interested in tau in doing that, looking at ways in which we can provide that type of functionality throughout the stack. It's also important to think about performance variation or performance stability or however you want to describe it, whereby just offline performance engineering, after execution, post-mortem, might not be enough. We might need to build more support within the system, within the tools to enable doing things online. That even further motivates the need for integration, tighter integration with the software stack, because there are things that are known by layers of the software stack that are not known by the tools. And that needs to have that type of integration, information exchange, knowledge exchange, policies, and so forth in order to enable this. And I want to do the last slide, which for more information, DKR already mentioned our Euro MPI paper. Aurel has a poster here, Aurel as well as Srinivasan, that talks about those two other aspects that I mentioned about this particular project, and I'm happy to take questions.